Merci, Monsieur le Président. D'abord, permettez-moi de remercier les membres du jury d'avoir accepté de juger mon travail. Je veux remercier aussi mon encadrant, M. Mourad, qui était toujours près de moi lors de la réalisation de cette thèse, à l'équipe de sciences de matière et des rayonnements, département de physique. Monsieur le Président, permettez-moi de présenter mon exposé en anglais. So, as Mr. President mentioned, my thesis is titled Quantum Entanglement and the Wigner Function Negativity. As you know, quantum entanglement is a key resource for many quantum technologies and quantum information processing. So, as in the classical case, also quantum information can be encoded using discrete variable systems and continuous variable systems. Several tools have been proposed to study quantum entanglement in discrete variable systems, and also many approaches have been developed for continuous variable systems, but all of them are proposed are extended from the discrete variable case and are limited only to the systems of Gaussian states. Beyond Gaussian states, any investigation of quantum entanglement will be more difficult and this investigation are proposed only for systems for special case of no-Gaussian states. So my presentation will begin with some backgrounds on information theory showing its classical case and its quantum version, focusing on the systems of continuous variables continuous variables and discrete variable systems. So, as a matter of fact, most popular entanglement identifying of continuous variable systems are founded in phase space based on the characteristic functions. And in order to quantify quantum correlation in continuous variable systems of no-Gaussian states, we have to introduce a complete and continuous function that brought the phase space representation into quantum physics and has a unique nature to identify the quantum behavior and the classical behavior. I'm talking about the Wigner function. So as we see, most entanglement criteria extended from the finite dimension systems and adequate only to study continuous variable systems of Gaussian states. But beyond Gaussian systems, there is a systems with no Gaussian states in which we are interested in this thesis to show the role of the Wigner function quantifying. First of all, one asks, what is information? So, information is an ordered symbol of sequences, and in order to interpret its meaning, the basic idea is to quantify this information as a form of entropy. So, what is this entropy? For example, here we have a system completely disordered and the entropy is at maximum. So, and in order to understand the relationship between the disorder concept and the entropy concept, I'm going to show you an example of 3 packets, and in these packets we have balls with different colors, and these balls are indistinguishable beside their colors. For example, let's now consider the entropy is how much we can rearrange these ball colors. For example, in the first packet, we have 1 possibility, and in the second packet, I have 4 possibilities, and in the last packet, I have 6. So I say that in the first packet, I have high knowledge, and the entropy is low, and in the packet at the middle, I have medium knowledge, and the entropy also is medium, and in the last packet, high knowledge with high entropy. Let's now consider another experience. Pick a read ball from packets. From the first packet, I'm picking a read ball for sure, and the probability is 1. But in the second packet, the probability is 3/4, and in the last packet, the probability decreases to 1/2. So I can say that the probability of winning is the product of the probabilities. And in the first packet, when we have high knowledge, the probability is at maximum. And in the last packets, we have low knowledge, and the probability is at minimum. So this product function is not a good function to define the entropy. What about sum? Using the logarithmic function. Okay, we say that in the first packet with high knowledge we have low entropy, and in the last packet where we have low knowledge, the entropy is at maximum. So the entropy is inversely proportional to the knowledge. And in order to generalize this definition, for example, if we have 5 red balls and 3 blue balls, and the experience is how much we can arrange these ball colors, the entropy here is given by the following formula. Generally, for n red ball and n blue ball, the entropy is given by. And for a discrete variable x with possible outcomes x1 to xn, which occur with the probabilities p1 to pn, the entropy is defined according to Claude-Shannon by the following sum. And in a quantum systems described by density matrix rho, this entropy can be defined by von Neumann entropy by the following trace. In order to study the properties of this entropy of von Neumann, I'm going to consider a quantum system described by density matrix rho A and another system living in the Hilbert space of dimension D2 and described by rho B. So the area covered by the green is the von Neumann entropy of the system A, and the area by red is the von Neumann entropy of the system B, and the area contained by both circles is the joint entropy of the total system, and the area at the left is the von Neumann entropy of the system A known B, and at right is of the system B known A, and the quantity at middle is the mutual information shared between both systems A and B. Now, in classical case, we have defined the information according to the ball's colors, where the state of the system can be 0, for example, red color, or 1, blue color. So the classical information encoded in 0 and 1, and this concept is defined by the byte or classical byte. What about quantum systems or quantum information? In the quantum case, we can call the quantity of information on an arbitrary superposed state of physical systems obeying the laws of quantum physics, for example, the energy levels or light polarization, vibrational trapping states, etc., etc. And similarly to the classical information, this quantity called quantum byte or Q byte, and pertinently, this quantity is the basis of quantum information and add value to quantum computation. Now, in order to study the properties of this entropy in the quantum world, I'm going to give 3 independent systems, A, B, and C, described by the 3 following states. Independent system means pure system. So the von Neumann entropy of H1 is 0. And this means that the total state is separable, so its von Neumann entropy is additive. If the entropy of the joint system is different to the sum of the entropies of its components, this means that the components are correlated and cannot describe it by a pure state. And when the total state is pure, will be with 0 entropy, but each subsystem has non-zero entropy when considered individually in its reduced density matrix. For mixed states, this leads to the strong additivity property of the von Neumann entropy. So the collective behavior of classical systems is determined by the way the subsystems interact among them and be correlated. And there is in quantum world a correlation don't have a counterpart in the classical world. In pure state, for example, all these correlations are nothing else but the quantum entanglement. And beyond entanglement, there is another type of correlations. These correlations appear when the total state is not a pure state. So the usual description of quantum system is the von Neumann approach, where each quantity in the quantum systems is associated to an operator. And of course, there is two types of operators, operators with continuous spectrum and operators with discrete spectrum. And quantum system of discrete state of dimension 2, for example, are the simplest and were the first considered and have led to implementing some quantum computation tasks with qubits. In particular, one of the most quantum systems used of discrete variable is the polarization of single photons. On the other hand, the first example of continuous variable system used in quantum information is the position and momentum of a particle. Its analog in quantum optics is the quadratic component of the electromagnetic field. And this analogy obtained from the quantization of the field that makes it possible to write a mode like a quantum harmonic oscillator. So in classical mechanics, for example, a system can be represented by a position vector in the Euclidean space. In the phase space, the possible state corresponding to one unique point, and this point, for example, for a simple harmonic motion, give a circle phase space trajectory. And a quantum system is, for example, quantum system of 2 degrees of freedom can be represented in the Hilbert space of dimension 2. So due to the Heisenberg uncertainty, this system is represented in the phase space by a spot instead of a point. In Hilbert space, a density matrix is an operator that describes the statistical state, whether pure or mixed, and the probability of any outcome of any well-defined measurement upon a system can be calculated from the density matrix of this system. The realization of this operator in phase space is a real function of phase space coordinate of the physical system under consideration. And the maps between the two spaces is defined by the Wigner-Weil transformation. A state described by density matrix rho is a Gaussian state if its characteristic function is Gaussian. And one of the fundamental properties of the Gaussian state, it's completely characterized by the first and the second moment of the quadratic operators. So consequently, to obtain rho, it's sufficient to know its first moment and its covariance matrix. Beside the characteristic function, there are another form of distribution function which can also represent the quantum states. One of them is the famous Wigner function. It is defined as the symplectic Fourier transform of the characteristic function. By projecting the Wigner function on one of the axes, the position axis or the momentum axis, we can obtain the marginal distribution associated with these systems. So for a quantum states, the marginal distributions are given as average values of the density matrix. So in this respect, the objective of quantum tomography is given to reconstruct the Wigner function by performing measurement on a very large number of sections. This Wigner satisfies all conditions of density operator except the positivity. And the Wigner function of a pure state can be calculated as follows. And using this following expression of the Wigner function of the pure state and the Wigner file transform of the tensor product operator, the total Wigner function of a separable state is a product of the sub-Wigner functions. And as we previously said, a Gaussian state is defined by a Gaussian characteristic function and can be characterized in the phase space by a Gaussian form of the Wigner function as a genuine probability distribution because it's positive over all phase space. For example, the vacuum state is a particular Gaussian state where all the quadrature's components have the same noise variance and the uncertainty region is a circle centered at the origin. So the second Gaussian quantum states that has property more closer to those of the classical field is the coherent state that is defined by the vacuum state displaced to location alpha in the phase space using the unitary displacement operator. And any phase shifting or any shifting in the field can be represented by a sample rotation in the phase space using the following operator. So for the vacuum, from the vacuum states, we can obtain also another class of states or another class of Gaussian states called squeezed vacuum states using the following squeezing operator. And similarly to the current state, this squeezed current state is generated by displacing the squeezed vacuum state by an amplitude alpha in the phase space. Let's come back to the positivity condition that Wigner function lacks to be a probability distribution. Here, this condition can be the most noticeable property and serve as an indicator of no classicality. For example, here, the no classicality is associated with the local correlations between the two state quadratures. On the other hand, there exists a single quantum states having no classical behavior, and this no classicality can be interpreted as photon anti-vanishing, for example. We say that some of these states are Gaussian and the others are not, in which case the Wigner function is negative. So in this context, Hudson gave a simple distinction between the Gaussian and non-Gaussian states based on the sign of the Wigner function. Hudson said a pure state characterized by a positive Wigner function is a Gaussian state. So in this context, several experimental protocols explore this non-Gaussian entangled state and make the generation of these states possible. The first step toward this entanglement distillation is to be able to transform a Gaussian state to a non-Gaussian state more entangled. Among the possible strategies used or most studied, there is the subtraction or the addition of photons from or to coherent states. And it has been shown that the final states in the ideal case are always more entangled than the starting states. This is the final state, and it is a no Gaussian state. This negativity appears in the final state can be quantified by the following integral, and also can be used as a measure of the no classicality degree in single mode systems. In single systems, the negativity of the Wigner function indicates the no classical nature of the state, but this no classicality is a local property due to the local behavior of quantum systems, superposition, photon anti-vanishing, etc. And in this thesis, we are interested Firstly, in the negativity of a single mode system as an indicator of no classicality. And for composite systems, we extend this negativity to the total Wigner to another interpretation in the context of quantum no locality. So in composite system, there exist local multimode systems with negative Wigner function. For example, the product Fuchs state or the product cut states, but also build state using the Fuchs basis is a no Gaussian state and has negative Wigner function. And the quasi-build state constructed use the coherent states also, it's no positive Wigner function. So the most simplest way to study any quantum system is to start from the pure state. In quantum information theory or in quantum computation or any field in quantum optics, the Gaussian multimode states are relatively simple to work theoretically and also usually produced in the laboratory. So they have been successfully applied to perform many important protocols. This advantage comes from the development of the optical Gaussian operations, but many investigations have been shown some limitation to the Gaussian states, such as quantum entanglement distillation. It's not possible with Gaussian states. Moreover, most of entanglement studies have been limited to this Gaussian states, where the entanglement degree is based on the behavior of the covariance matrix. And in both classes, there is no local correlations. As we are in the pure case, these correlations are nothing else but quantum entanglement. And this, in this case, the quantifiers of quantum entanglement are fairly valid in the systems of no Gaussian states, and they are only limited to the Gaussian systems. For such reasons, we have contributed in recent published works to activities by investigation the Wigner function properties. And you may know that in the systems of no Gaussian states, the Wigner function exhibit negative values even for separable states. And this could imply that such observed negativity on the Wigner function cannot be described directly as an indicator of entanglement, because can be negative for separable state also. In this context, we present a new approach to quantify geometrically the entanglement in no Gaussian states, showing the connectivity of this entanglement with the Wigner function negativity. So let rho be a Gaussian state and rho s a separable state, and rho is a given entangled state. This state contains two kinds of no Gaussianity: local and non-local no Gaussianity. In terms of any geometrical measure of the no Gaussianity of the state, and the equation is the distance to the nearest Gaussian state. In multimode systems, this distance can be divided to the local and non-local no Gaussianity. And in terms of the Wigner function negativity, the first quantity can be quantified by the negative volume of the separable state, and the second negativity is due to the non-local behavior of the state, that is nothing else but the quantum entanglement amount in this total state. And this amount can be defined by the following formula with a minimization on the nearest separable states. Or directly using the Wigner functions of the total and the nearest separable states. This quantity must satisfy the properties of distance. First, between 2 points is 0, if the 2 points coincide. And second, it's always positive and satisfy the subadditivity property and the symmetry property. If we say this quantity as a quantum entanglement quantifier, it must satisfy the following lemmas: if and only it's equal to 0 if and only rho is separable and cannot increase in the local operations and classical communications. So as there is no computable measure of no-Gaussian entanglement, and in order to evaluate our approach as a measure of quantum entanglement, we need to use a numerical program to diagonalize numerically the density matrix of high dimension, or we can use the well-known discrete variable measures, but in this case, a diagonal basis is needed. As an application of our approach, we choose to analyze first the entanglement of some relevant bipartite systems, beginning by the generalized known states, or called large photon number entangled states. A known state is a quantum many-body entangled state of n-particle systems and has an important concept in quantum metrology and quantum detection for their ability to perform precision phase measurement when used in the optical interferometers. So using Wigner function of the two-mode Fock state, we can easily find that of the known state. To show the link between our quantity and the entanglement in no-Gaussian systems, we have to show the Wigner function's properties or profiles of the state under consideration and the Wigner function of the nearest separable states. For example, for the known state, fixing gamma in 0 or 1, for any photon number, the state is separable, and the Wigner function is still no Gaussian. So this means that it has some negative part, and according to the meaning of the Wigner function negativity discussed before, it is clear to say that this negative part that appears here can be interpreted as local correlations due to the no classical behavior of Fock number state associated to single modes. And from the plot at right, we know that the Wigner function of the known state has several negative regions, and these regions are symmetric, which allows us to suggest that this symmetric negativity of the Wigner function due to the interference effect between the two modes, which means that this behavior of the Wigner function depends not only to the local correlations between one mode quadratures, but it depends on the no local correlations between the quadratures of the two modes as well. And this value of gamma equal 1 over square root 2. It's not chosen arbitrary, but it's the value that maximizes the quantum entanglement in the known states. And in order to discuss the similarity between our quantity and the entanglement, we show both as a function of gamma using the Paris negativity. These plots show that the quantity delta increase with probability amplitude to attain the maximum value obtained for gamma equal 1 over square root 2, and separable for gamma equal 0 and 1. This happens for any photon number selected. The second application of our approach is to two-mode squeezing vortex state. There are many methods for producing this state. One of them is by mixing two squeezed vacuum modes through beam splitters. And the other one is by photon subtraction or addition. If an arbitrary number of photons are subtracted from the two-mode squeezed vacuum state, this state can be generalized to the following form. According to the following transformation, its Wigner function can be expressed as. So in these states, we see that the interference effects depend on the squeezing parameter R and on the number of photons. Here we plot the same quantities for the two-mode squeeze and vortex states, and these quantities are shown as a function of the squeeze parameter R. It is observed from the last plot that the entanglement in this state is reduced with the number of photons, and for a fixed photon number, the entanglement degree starts with a very small rise which falls smoothly after reaching the peak. Similarly to the Bell states, in continuous variables world, there is the quasi-Bell states are similar to the Bell state constructed using the current states. And in order to manipulate this kind of states in quantum computation or in other similar applications, we need quantum gates acting on no diagonal basis. Many techniques have been proposed based on the orthogonal basis of the even and odd current states. But despite all that, it will be much difficult to realize quantum gates in the with the macroscopic qubits. And using the Wigner function of the pure current states to calculate that of the two-mode quasi-Bell state. So we see that for alpha different to 0, the Wigner function of this state is negative over all phase space, and this negativity may be due to the entanglement in these states or due to the local correlation between the quadratures of single modes. And both quantities graphs show that the negativity equal to the 0 for alpha equal 0, and where the Wigner function is a sample product of two vacuum mode states and increase with increasing values of the parameter alpha to reach its maximum, then stabilize in the maximum value for large values of alpha. So it's here in the for the large values of alpha, the current state alpha and minus alpha be orthogonal, and the quasi-Bell state has the same behavior of the Bell state in discrete variable entanglement, which is maximally entangled. This basis of evidence suggests that our quantity would lend itself well for use as an entanglement measure for bipartite no Gaussian systems. What about multimode systems? In n-mode systems, where n more than 2, the classification of entangled states is richer than in bipartite systems. As a matter of fact, in multimode systems, there is entangled states, separable states, re-entangled states, and genuine entangled states. Let's consider three systems. We suppose that the system AB and AC are maximally entangled. Then the system A could explode both channels simultaneously. This can be formulated mathematically by Kaufman, Kondo, and Waters' inequality. Considering three qubits, each one can be entangled with others. And the entanglement shared between system 1 and 2, 3 as a single system is always greater than the entanglement shared separately. This means no sharing for maximal entanglement, but no maximal one can be shared. This is a fundamental quantum property called the monogamy. Its realization is dependent on the entanglement measure chosen. This property can be generalized to the multimode systems of n qubit following the same construction. The more general way is to use the block entanglement decomposing. In this kind of systems, the genuine entanglement quantifier mostly used is the genuine tangle, defined as the difference between bipartite entanglement existing between one subsystem and the others considered as a single entity, and the sum of all bipartite entanglement existing between the subsystems. A minimization, of course, on this construction is needed. For example, in tripartite systems, the genuine entanglement is represented by the following quantity, and for bipartite by this, and in multipartite systems is represented by the last representation. Let's choose the tripartite case because it's the simplest one, where the genuine entanglement is a minimization on the three following constructions. Using the concurrence, this quantity can be expressed mathematically as. Let's come back to apply our approach in this multipartite world. Using the generalized three-mode coherent states to build the major class of tripartite states, that is the GHZ class. Its Wigner function is implicitly depend on 6 quadratures in addition to the current state uploaded. So in this slide, we showed the variation of the different type of entanglement against the parameter alpha. To make clear, we plot the Wigner function of the states for selected positions and momenta animated versus unplotted. We say that the bipartite entanglement increases with increasing values of the parameter alpha to reach its maximum value, then decrease slowly with increasing values of alpha to disappear for large values of the current unplotted. Furthermore, it is seen that both the tripartite and genuine entanglement increase with the increasing values of the current state unplotted, and for large values of alpha, the tripartite entanglement becomes equal to genuine entanglement and both attain their maximum value. It's worldwide motion that the states alpha and mains alpha become orthogonal, and thus the behavior of the GHZ coherent states is exactly that of the GHZ in the discrete variable systems or in the orthogonal basis. Namely, for this particular case, there is no bipartite entanglement, but the state possesses maximal genuine entanglement. For the bipartite case, we know that the quantity delta for the reduced state has the same behavior of the bipartite entanglement. This consequence reveals that the quantity delta of reduced state can be served as a bipartite entanglement monotone, which confirms the result obtained in the bipartite systems studied previously. But the Wigner function of the total state has the same behavior of tripartite entanglement and of genuine entanglement, which are both tending to their maximum values for large amplitude. So to decide which one of these two types of entanglement our quantity is a good quantifier of, we have to introduce another class of continuous variable states, is the W current states class, where the genuine entanglement is absent and the quantity delta equal to 0 for all values of alpha. According to this result, we can settle on the fact that the quantity delta of a total multipartite system in a pure state can be interpreted as a genuine entanglement quantifier. So now we can say that this approach is a direct quantifying of genuine entanglement independent from any bipartite constructions. As conclusion, in this thesis, we address the issue of entanglement identifying in discrete and continuous variable systems, providing a new approaches to quantify the entanglement in continuous variable states. We introduce and develop a geometric measure of entanglement in continuous variable systems for the class of no-Gaussian pure states based on the negativity property of the Wigner function. In this dissertation, we found that for two-mode non-Gaussian entangled pure states, the negativity of the Wigner function can be interpreted as an indicator of no local correlations. And according to this finding, we have developed a geometric entanglement quantifier for the set of no-Gaussian states. We showed that our quantity satisfies the neutral properties expected from a good entanglement monotone. This approach has extended to the case of multipartite systems of pure states as quantifier of genuine entanglement. However, the findings of the current study might not be generalized to all classes of states. A number of potential limitations and weak points need to be considered. First, our investigation into this area is specifically designed for the class of pure states and not for mixed states. Secondly, the entanglement measure was defined only for no Gaussian states and not for Gaussian states, but we are confident that our result will serve as a basis for future studies in the no Gaussian entanglement in phase space and should be extended and validated by large classes of states. For this reason, we are currently in the process of investigating this entanglement or this approach for the systems of mixed state and in the systems of discrete variables, and for hybrid systems, why not? So as application on the experimental level, our approach served to manipulate the no-Gaussian entanglement distillation protocols, which is a task that cannot be realized using Gaussian states, and quantifying the degree of entanglement in cut states, which are the basis of quantum gates, and manipulate the added or subtracted photons coherent state used in quantum K distribution to increase the fidelity of quantum channels. So this thesis is based on the following research publications realized in ESMaR team. It was a great honor to collaborate with these wonderful professors and the PhD students. This is an opportunity to thank all of them for their assistance. And I would like to thank very much to accept to be jury members of this thesis. And thank you for your attention.